Hello, class. Welcome back to a series of lessons on stoichiometry. In the last lesson, we covered balancing chemical equations and the law of conservation of matter. And now we're moving on to mole ratios and gram-to-gram conversions. So this will allow us to calculate different quantities of materials consumed and produced in chemical reactions, which is the definition of stoichiometry to begin with. So first, a mole ratio is based off of the coefficients of a known substance A and the coefficient of a desired unknown substance B. And we can use those to convert. So if I'm looking at a balanced chemical equation, first we are usually given some mass in grams. When we have our mass in grams, we know we must convert it to moles in order to compare them. Once they're in moles, we can use the mole ratio from our balanced chemical equation to convert from one substance to another within that chemical equation. And then, of course, once we're in moles of that new substance, we can convert back to grams. So moles of the desired substance B is on top, and moles of the known substance A is on the bottom of my dimensional analysis fraction. So let's take a look at an example, and I'll let you work through a couple together. So solid lithium hydroxide, we'll come up with our balanced equation as we go. Lithium has a +1 charge, OH has a -1 charge, so this is LiOH, is used in space vehicles to remove exhaled carbon dioxide from the environment by forming lithium carbonate and liquid water. So if we're removing CO2, that means CO2 is a reactant. And then lithium carbonate, so Li is a 1+ charge. Carbonate, CO3 is a 2- charge, so I need a 2 here. Form solid lithium carbonate and then liquid water. What mass of gaseous carbon dioxide can be absorbed by 1 kilogram of lithium hydroxide? So first, let's go through and balance, and then we can talk about the dimensional analysis. So I see 1 lithium on the left, 2 on the right. I need a 2 here to balance that out. By putting a 2 there, that also gives me 2 oxygen here plus the 2 oxygen here, which means I have 4 total on the left. I have 3 and 1, which makes 4 total on the right. This also gives me 2 hydrogen on the left, 2 hydrogen on the right, 1 carbon, and 1 carbon. So really, I just needed to put a 2 there, and I have balanced out my equation. All right, and let me clean this up a little bit. I think I lost a 3 in my coefficient here. And again, you can just put 1s in the blanks for the other ones. I do encourage this because this is going to help you with your mole ratio. All right, so I have 1 kilogram of lithium hydroxide, and there's 3 significant figures there. Now, kilograms is not really useful for us, so my first step is to work in some metric conversions. 1 kilogram I know is equal to 1,000 grams. So I'm going to convert it to grams first, and then I can do my gram to mole conversion. If I have grams on the top of my second fraction here, because kilograms have canceled, then I need grams of lithium hydroxide on the bottom. All right. And then on top would be 1 mole of lithium hydroxide. Now I need to find my molar mass, so I got to break out my calculator. Lithium, I believe, has a molar mass of 6.93. 6.94, my bad. 6.94 plus 16 for oxygen and 1.01 for hydrogen. My molar mass of lithium hydroxide is going to be 23.95 grams. All right, now here's where the mole ratio comes into. I want to know the mass of carbon dioxide. So before I can find the mass of my unknown carbon dioxide, I have to find the moles of my carbon dioxide. So just like I did up top, the mole of your desired substance CO2 must go on top, and the moles of your current substance that you know must go on the bottom. In my second step here, grams will cancel and I'll be left in moles of lithium hydroxide, so it makes sense to put moles of lithium hydroxide on the bottom because that will cancel out. Now my coefficient here, this is where it's tricky and people get confused. My coefficient is what goes on this fraction. I have 2 moles from my coefficient here, and then I have 1 mole of carbon dioxide. So 2 moles for every 1 mole, it's part of my recipe. When you have a mole and mole conversion, so this fraction step, that's the only one where the mole number can be something other than 1. When you're doing a gram to mole conversion, gram and mole conversions, mole should always be 1 because that is derived from the unit gram per mole. When we say gram per mole, that's grams per 1 mole. So keep that in mind. Mole can only be 1 when you're doing a gram and mole conversion. It can be something other than 1 when you're doing a mole to mole conversion. Now that we're in moles of CO2, I can convert back to grams of CO2, so 1 mole of CO2, and then my molar mass of CO2 is 44.01 grams per mole. We can double check that if you like, 12.01 for carbon plus 16 times 2, and we get 44.01. All right, so now let's go ahead, double check our units. Everything cancels appropriately, moles is gone, and I'm left in grams of CO2 as my final answer. Based off of my original answer, or my original quantity of 1 kilogram, I have 3 significant figures here. So my final answer should have 3 significant figures. So 1.00 times 1,000 over 1, close parentheses, times 1 over 23.95, close parentheses, times 1/2 for my mole ratio, close parentheses, times 44.01 divided by 1, close parentheses. And I get an answer of 918.789, yada, yada, yada. Now, if I have 3 significant figures, the 9 is significant, the 1 is significant, and the 8 is significant, but I need to look to the 7 to figure out if I need to round up or down. Since there's a 7 in that tens place, that would round up to 919 grams of CO2. And this would be 3 significant figures, and that is how many grams of carbon dioxide can be absorbed. Now, you can do the same problem with any of the quantities in the reaction. If I want to know what mass of lithium carbonate I have, I can do the same thing. I just need to change my mole ratio so that the mass of my desired amount is on top. So it would say 1 mole of lithium carbonate. Or I could figure out the mass of water, 1 mole of water on top. And then you need to change your molar masses to correspond to whatever compound you are trying to calculate. All right, go ahead and try these next couple of problems. You need to balance them first and then convert to grams of whatever compound they are asking. All right, welcome back. One thing I wanted to talk about, let me see my time. Yeah, we got plenty of time. I want to talk about the conceptual analysis of mole ratios and reactions. Baking soda is often used as an antacid. It neutralizes excess hydrochloric acid secreted by the stomach. Milk of magnesia, which is an aqueous suspension of magnesium hydroxide, is also used as an antacid. I believe milk of magnesia is the same thing as Mylanta, if you're familiar with Mylanta. Let me double check that real quick. You might have encountered that before as well. Yep, it's actually a mixture of magnesium hydroxide and a couple of other things, but Mylanta is very similar to milk of magnesia. So then this question is asking which is more effective, the more effective antacid per gram, NaHCO3 or MgOH2? Justify your answer. Well, we got to look at a couple of things here. We got to look at both the molar masses and the mole ratios. So just by looking at the moles of magnesium hydroxide compared to the moles of HCl, I would say that magnesium hydroxide would be more effective because 1 mole of magnesium hydroxide reacts with 2 moles of hydrochloric acid, whereas sodium bicarbonate, which is baking soda, only reacts with 1 mole of acid. So you're neutralizing twice as much acid for every 1 mole that you have compared to the baking soda. So one of the things we can do is evaluate their molar masses and figure out, okay, if I have 1 mole of each, which one is more effective per gram? So magnesium, calculate the molar mass of magnesium hydroxide. Magnesium is 24.31, check that on the periodic table. 16 times 2 for your oxygen, plus 1.01 for your hydrogen times 2. So I have a molar mass of 58.33 grams per mole. And then for sodium bicarbonate, I have 22.99 for sodium, plus 1.01 for hydrogen, plus 12.01 for carbon, plus 16 times 3. Which gives me 84.01 grams per mole for sodium bicarbonate. So there's 2 things in play here. We're comparing equal mole amounts, and if we're looking per gram, which is what the question is asking, magnesium hydroxide has a smaller mass per mole. So if you have the same amount of moles, you are getting way more bang for your buck when you're looking at magnesium hydroxide than you are for sodium bicarbonate. 1, because sodium bicarbonate is heavier for each mole that you have, and 2, because we're reacting 2 moles of HCl for every 1 mole of magnesium hydroxide. Here you're only reacting 1 mole of each. So if I wanted to react 2 moles of HCl with baking soda, I would have to double this amount, and I would actually have to use somewhere in the realm of 168 grams per mole to neutralize 2 moles of HCl, because I want to neutralize the same amount as the magnesium hydroxide is. So magnesium hydroxide would be the more effective one here for 2 reasons. 1, because of its mass, and 2, because of how many moles of HCl are neutralized in the course of the reaction. This is a common question type on the free responses in AP Chemistry, where they ask you to analyze which one would be more effective at some sort of treatment, depending on what phenomena they're looking at. And most often you can get the correct answer just by looking at the mole ratio, but be careful if they're asking per gram. Typically they just ask which is more effective. If this problem did not say per gram, I would say just look at the mole ratio. There's 2 moles being neutralized of HCl for every 1 mole of magnesium hydroxide, whereas the other one only neutralizes 1 mole. And so you need less material to neutralize this more stuff. And so that would be the better answer. Okay, and let's check on our time. All right, so we got about 5 minutes. What I can do in this lesson is start talking about limiting reactants from a conceptual standpoint, and then in the next lesson we'll go over the calculations. So a limiting reactant, here's a particle diagram, and you should fill this out as we go. This reaction is actually a picture before the reactions take place. It's the reaction of nitrogen gas and hydrogen gas to form NH3. So how many N2 particles are in the container? I count 1, 2, 3, 4, 5. And then how many H2 particles are there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. All right. So if I've got 15 and 5, the next question says, if one N2 molecule reacts with 3 H2 particles, how many times can you complete the reaction in this container? Circle the number of groups to confirm. So I need to circle the combination that is 3 H2 and 1 N2. So I see a group here that could react. I see a group here that could react. I see a group here. I see a group here and a group here. So it looks like I can complete this reaction 5 times in total. Okay, so make sure you've got those down. And let's talk about what's happening here. So there are 5 and 15 of each particle at the beginning of the reaction. All of the hydrogen and nitrogen atoms combine to make, I told you at the beginning, it makes NH3. So this makes NH3 particles. There are no particles left over. If we have leftovers, we're going to use the term excess. So there is no excess here. The reaction has been completed 5 times. Each time the reaction is completed, we want to figure out how many particles are made. So that's a great question. So what we really need is a balance of N2 plus H2 yields NH3. So to balance this out, if I have a 2 here, and we said 3 and 1 was our ratio, right? So 3 times 2 is 6 for hydrogen. I've got 6 hydrogens on each side. I've got 2 nitrogens on each side. So each time the reaction is completed, 2 particles of NH3 are made. So I should say 2 NH3 particles are made. Since the reaction has been completed 5 times, 2 times 5 is 10. We have 10 NH3 particles that are made total. This is considered, we can say the term perfect stoichiometry. Perfect stoichiometry, or you can say complete stoichiometry, something to that effect, where the ratios are perfect so that there's no excess reactants or no excess reactants after the duration of the reaction. Now that's container 1. What happens if it is not perfect stoichiometry? What happens if the ratios are not balanced? Let's look at this container. Let's see, I've got 1, 2, 3, 4, 5 nitrogen particles again, but this time I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, it looks like. 1, 2, 3, 4, 5, 6, 7, 8, 9. I got 9 H2 particles. If 1 N2 reacts with 3 H2, how many times can we complete this reaction? Well, let's go ahead and circle again. I see 1, I see 2, and then maybe this one, 3. So we can only complete this 3 times. And then it says how many particles are left over. We don't have any H2 left over, but we do have 2 N2 left over. So originally we have 5 nitrogen and 9 hydrogen. The reaction is only completed 3 times. There are 2 particles of nitrogen left over. Actually, sorry. The term, if I read carefully, in excess is the term. I mentioned that before. We want to use the term excess. And then hydrogen runs out first. So it is what is called the limiting reactant. So this is important, this key idea that if you have perfect stoichiometry or a perfect reaction, everything gets used up, there's nothing left over, nothing limits the reaction or how many particles can be formed. However, if there's an imbalance and it doesn't follow your recipe or your balanced equation, then you have imperfect stoichiometry, or what is called a limiting reactant situation. The course of the reaction is limited by the component that gets used up first. So since this reaction completed 3 times, 3 times 2 is 6 from my balanced equation, there were only 6 NH3 particles produced. So what happens is if I were to draw a container, and I'll keep the colors the same. So I've got I said 6 particles, right? 1, 2, 3, 4, 5, 6. And then each of these is going to have 3 hydrogens attached. 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. My new container would have 6 NH3 molecules, which is what I just drew here. And then there are still going to be 2 N2 molecules hanging out in blue here. And those are going to be leftovers in your container. So it's really important to note that using particle diagrams like this is something you will be expected to do, and you'll have to analyze them for stoichiometry purposes. So identifying what the products look like, and then also identifying what's left over in the container to maintain your law of conservation of matter is really, really important here. H2 is considered the limiting reactant because it runs out first. N2 is considered in excess because there's extra. So excess, extra, that's the way I remember it. When we apply this in the next lesson, we'll actually use gram to gram conversions like we did earlier on in this lesson to calculate and predict which one actually will be in excess. Particle diagrams are great, but when you're looking at something in the lab on the bulk scale, you need to be able to predict which one will run out first. All right, that is all for this lesson. I'll see you in the next one.